Okay, ladies and gentlemen, so at this time we're just about ready to start the Open Science Slam. Now, to just talk briefly about the rules of the Science Slam. It's not like a traditional Science Slam. We don't really have any real rules. It's just that we invited so many people from all around the world studying many different interesting topics, and whoever would like to present his or her topic or some interesting stuff that they're working on is welcome to do so. So just come up here and talk to us. If you have a presentation, that's fine, like as PowerPoint slides or whatever. If you don't, that's also fine. You can just talk about it. And whoever wants to participate also gets a small present from us. So just to get us started, it's our very own Ratze.
Okay. Hello, everybody. Yeah, nice to have this chance to present again. It's kind of interesting that the people are starting here in the 5th row or something. Am I smelling that hard? I don't know. But let us go over this. I would like to present my research topic, and I think you all can read. My title is, I have an ultra short one. And to be honest, yeah, I want to speak today with you about electrons and atoms, as you may imagine. So the most of you now try to not vomit about hearing chemistry and such stuff again, so I try to make it more introductive with this kind of model. So think about, come in my world of atoms and electrons, and think the atom is this house, the electron sits in there, and to make this picture more familiar to you, I would say the electron is a student. And the student in the ground state, you are students, the most of you, the student in the ground state lies in the bed, we all know that. So the energy is 0, as you see here, on this energy scale on the left side. And what we are doing now with our experiments, so this is some physics stuff. Most of you don't deal with this stuff all day long, so I try to introduce it. What we do is we shine ultraviolet light on this, with a laser pulse, ultraviolet. And the most of you know it, you heard it about, you can get your skin burned by that. But what is ultraviolet light? What is, to explain it a little bit, I make a picture, and maybe this picture is easier for that. Think about that we give an energy drink, for this soft drink from Red Bull, you may know it, to this electron. In my childhood I saw an advertising about that, and they said if you drink this energy drink, you will get wings on your back and fly away. And think about it in the same way for our electron. So if you drink an energy drink while lying in the bed, I think you cannot sleep anymore. And the electron is now able to leave was there something? Somebody asking something? Okay, good, I continue. The idea is now to leave the house, to leave the atom, and the electron can now fly away to the sky. Fly away, fly away. Okay, good. There it comes. Okay, now the electron is above there. We now measure it while trapping the electron like this. And we call that photo-emission spectroscopy. And I just put a formula in there to look at least some that I'm intelligent. Okay, good. You now may ask, okay, he's doing some boring physics, so what? Okay. I would like to explain it to you. As I said, just a small reminder, we will do the test later on. The electron was in the ground state, we put the light on the electron, this ultraviolet energy drink light. The electron got some more energy and we could measure it. What we do now in addition to make it more funny, because this stuff was done 30 years ago as well, is we shine red light on it. And some of you heard physics and know the red light is not that energy containing like ultraviolet light, so not an energy drink. Let's think about a coffee. So we now give the coffee to the electron. The electron is still not able to leave the house while flying away, doesn't get any wings, but it also cannot sleep anymore. So the electron is now excited, like you as you're drinking a coffee. And then we do the same thing again. We also shine the ultraviolet light on it, and can measure the electron in the excited state. So, yeah, now you know not much more than 2 seconds before. And me as myself, as doing some basic research, we have to explain ourselves a lot to parents, to other scientists. So the most of the people are asking, for what we do need that? And the idea is very simple. This excited state we create there is kind of similar to a voltage we put on a material, like a conductor, whatever. And I don't know how familiar you are with that, but yeah, this is a resistance. We put a voltage into that, and then in a conductor, the electrons run through this material. They, yeah, move, and we call this a current. Yeah, some of you may heard that. That's what happens if you put a switch on the light, and that's okay. That's fine. And this is kind of similar to this excited state. But what we are interested about is what happens to this electron. Now think as yourself as an electron. You now want to leave the house. You are excited to go to a lecture. This happens 1 or 2 times in the life of a student, as far as I know. And you're now on the way to the lecture hall and want to hear the lecture. But what happens on the way to there? You meet other students, you meet other electrons, and yeah, you drink a coffee together, and we call this scattering. So you give some energy to the others, take some time, you are delayed, and this happens sometime to the way to your lecture hall, and it happens more times, and you lose energy on the way to your lecture hall to hear the talk of the professor, and you're very late at the end, and yeah, you're losing this energy. So we would say this electron has some kind of lifetime, and while losing energy, and we call this electron scattering. I'm sorry for the spelling mistake here. And this is energy loss. Energy loss is something bad, okay? And for that, we now do our experiment. But you still ask, what has this to do with the title of my talk, which I mentioned earlier? That's also kind of simple, because this lifetime we want to measure, these electrons are goddamn fast. And so we have to be faster. And to do that, I use my ultra-short laser pulse. As a laser pulse, just for a definition, what is a laser pulse? Like I have this laser pointer here in my hand. There is an off state, so I don't push the button, and then I go to this on state, this energy drink laser pulse, and we're getting the electrons out there, and then I turn it off again, and this time, this pulse duration is our ultra-short laser pulse, and in our case, it's 0.0000000000000000001 seconds long. And yeah, I have to admit, it looks the same number appears also on my bank account. And in we scientists, we call this 10 to the minus 15 seconds. And this is also called 1 femtosecond. Most of you don't know that, so I try to explain this a little more on a logarithmic time scale. So people who don't like math, please don't leave the room. Okay, these are the 3-4 guys there. You like math? Please say it. Good. Good. This is a logarithmic timescale, so in exponents of 10. And I try to explain it a little bit more in this time scale. So 1 second you have here, and you're 10 to the 9. 10 to the 9 seconds is the human lifetime around of 70 years. Luckily, we live that long right now. Your studies you did around 3 years, these are 10 to the 7 or 10 to the 8 seconds. Going a little shorter, one exam within that is 10 to the 3 seconds. The same time, but it feels not that long, is sex. While having sex, many people can do it quite faster than half an hour I put here. And going on, human heartbeat, around 1 second. Going further down, a flash in a thunderstorm, whatever, is around 10 to the minus 5 seconds. And now you already maybe got some kind of thing. It has something to do with these electrons I mentioned before. Yeah, you have the feeling this has something to do with that. The same if you have your smartphone or your PC or your Mac or whatever, having a gigahertz electronic in there. This electronics works with 10 to the minus 9 seconds. Also something to do with electrons. Okay, electrons is also in the name. A chemical reaction is, okay, I again did a spelling mistake, sorry. Here is the all well-known cola and Mentos experiment. Is 10 to minus 12 seconds, and this has also something to do with these electrons, and therefore we do our laser with 10 to minus 15 femtoseconds. So we are faster than every one of these guys, and so we can measure that. We can celebrate now, we can measure our electrons, and we can measure everything of that, so we are cool. And yeah, here is actually a graph from my master's thesis. Just a very simple one, but I think it's quite easy. And it's what I told you before. So we start before here in this ground state, lying in the bed. Then at this time 0, so this is a time axis of delay. So here you see this femtoseconds, delay time. And at time 0, this laser pulse comes. This is the coffee one. So here the coffee comes, and then the electron is excited at this point. And from this point, the electron goes to the lecture, as I said, and gets scattered. And this happens down here. So the electron losing energy, this graph is about that, more or less. And we are interested in this way here. How are the processes to lose energy for electrons? And yeah, okay, I forgot that. While doing this, all these points are made by this energy drink pulse. This we use to measure, as I said before. Okay, and if you look up this experiment in the literature, you will find this is actually, that's no joke, called hot electron excitation. And yeah, in this case, I would like to summarize our research we do. This was with the coffee pulse, with the ultraviolet laser pulse, exciting these electrons. We do this to get some better electronics. I mean, we try to improve the scattering, make it better, make the energy loss lower. For that, everybody knows your smartphone battery is empty in 1 day or even shorter. So we try to get our battery better, or save energy in general. And with that, we all know the girls get happy. So I would like to summarize, because I have an ultra short one, the girls get happy. Good. Thanks for your attention.
Thank you very much. And of course, because you participated, you get some snacks for the way. And of course, the very important ISWI Naut button. You're not an astronaut, you're an ISWI Naut.
Thank you.
Thanks, Ratze.
Thank you.